So as I said at the start, my name is Andrew Sotarelli. I am an application engineer here at nTopology, located in our German office in not so sunny Regensburg. And joining me today is Jack Edgerton from D&G Mori. And today we'll talk a bit about how we can leverage the advantages of nTop platform to generate soft draws that will be suitable for doing subtractive post-processing. So we'll give a bit of an overview at the start of nTopology as well as D&G Mori. We'll discuss the manufacturing process for a specific part. In this case, we went with Femoral Stem and how you can leverage soft draws in that manufacturing process. And most importantly, for me, from the software side, we'll talk about how nTop platform can help solve some of these complex geometry problems. And then at the end, we'll do a little bit of an in-product demo and follow it up with a question and answer session. So a bit of background on nTopology as a company. nTopology has been around for approximately 4 years. We had our first commercial product in 2017 with nTop Elements, and we most recently launched nTop Platform in the spring of 2019 with our launch of nTop Platform 2.0, which included toolkits to simplify workflows like creating soft draws at Formnext this past year. And so really the goal of nTopology is to provide engineers with unprecedented modeling capabilities to solve complex geometric problems that you can't do with traditional modeling tools, creating complexity that traditional manufacturing methods may not have been able to deal with, but now can, such as those through additive manufacturing. And so really the industries that we see nTopology getting adopted into is aerospace, medical, automotive, and consumer products. We see that the level of complexity of parts that we can design with nTop platform fits really well with a lot of these industries. And so today we'll talk through a specific example where we're going to walk through the design of a medical component, in this case a femoral stem, and how we could use nTop platform as well as D&G Mori's manufacturing capabilities to generate that part from design to finished manufacturing products. And so how do we accomplish this goal of providing these unprecedented modeling capabilities to solve these complex problems that you can't traditionally do with your standard engineering tools? Well, it's through this computational modeling platform that combines design, simulation, as well as advanced manufacturing. And so we take this approach called field-driven design, where we can take in fields of data, which can be anything from simulation results to images to simply CSV files with data that vary spatially, and use that to drive the design of our products. And all of this is packaged into what we call replayable engineering workflows. So what we'll see today is using a replayable workflow to generate soft draws, not just for the femoral stem that Jack has gone ahead and manufactured for us, but also for almost any other product that you could think of. And so really the reason that nTop platform is coming on the market is we have these new advanced manufacturing technologies like additive manufacturing that can generate parts with unprecedented complexity and in designs that we never could have imagined. And the current design tools simply don't fit the bill in terms of allowing you to fully capture the capabilities of your manufacturing process. And along with this, we're seeing the need to distill and capture engineering knowledge and better leverage that knowledge to allow us to become more competitive companies. And so now I'll hand it over to Jack to talk a bit about D&G Mori and the process he went through to manufacture the part we chose today.
Thanks, Andrew. So today I'm going to talk a little bit about additive versus subtractive manufacturing and kind of how they can benefit one another, and then apply that to our particular application of manufacturing the femoral stem for a hip implant. So to start, one of the questions that I get most commonly at trade shows is whether or not I believe that additive is going to replace subtractive manufacturing methods. And my answer is always no. While there are definitely cases where we can consolidate manufacturing using additive, both methods have their own pros that will keep them in the game indefinitely. So why would we use additive in the first place? In a general sense, this isn't a comprehensive list by any means, but for freedom of design, what I mean by that is essentially you can make very, very complex geometries and features because you don't need to worry about tool access like you would in a subtractive platform. Additionally, within the manufacturing process, you don't need to do any sort of CAM work on the front end to create a toolpath for your part. So it's a lot easier to make changes to your design and then bring that straight to your manufacturing floor. And what that does is it allows you to get very rapid design iterations done to just increase the overall speed of your R&D for a new product. Now this does come with like some limitations. Ultimately, because it is a powder-based process, you're going to have a hard limitation on what surface finishes you can achieve. Additionally, you'll have a little bit tighter tolerances with the subtractive platform. So what we suggest is for these critical surfaces that might experience wear or friction, or maybe you just have a very tight tolerance on your spec for that feature, you could simply overbuild in that area and then machine down to your nominal geometry using a subtractive manufacturing method. And what you can see on the right here is actually our new LT30 SLM dual laser system. So getting into our actual use case here, this is the femoral stem that Andrew had previously mentioned. It was designed by an Anthropology senior applications engineer by the name of Christopher Cho. So big thanks to Chris for this awesome part design. So why would we produce this in additive? You can see on the bottom, there's a very fine randomized lattice structure that we'll refer to as a trabecular lattice. And what I mean by that is essentially it's mimicking the mechanical behavior of the trabecular or inner porous region of your bones. So what this does for us is it allows us to drive down the weight and stiffness of the part, hypothetically provide area for bone ingrowth. And then also because you're using an additive process, you would be able to tailor the size of the part through scaling so that it fits the individual as best as possible. Now, once we have this part printed, we're not completely finished. This is just one piece of a greater assembly that would go into a full hip replacement. So you would need to attach it to a femoral head, which is essentially like the ball of your hip, if you can imagine that. In order to do so, you would need a very fine surface for your mating surface, which would be the top of the stem. And additionally, you would have to have a tight tolerance. So after printing, you would bring this into your machining center to buzz down the surface finish for your mating surface. Now the challenge of this becomes, how do I hold a part that has somewhat abnormal geometry and additionally is in several different sizes potentially? It becomes a bit of an issue because you can't get a final functional prototype until you've more or less nailed down the design of your part. You're not going to want to invest the time and money into establishing a work holding method when you're planning additional design iterations in the future. So that kind of brings me into another piece of subtractive manufacturing that isn't always considered. It's the pain points of work holding. If you get to the point where you're doing a subtractive operation and you're just not holding your part tight enough, it's not giving you the surface finish that you'd like, there's too much chatter, you may come to the point where you don't have anything internally to use for your work holding. In most cases, what I've seen in the past is the customer would then go to an external vendor to outsource their work holding problems. Obviously, working through an external vendor is going to drive up the cost of your manufacturing process a fair amount and increase the lead time to get to the final stage of your part. Furthermore, if you're using some sort of a customized piece, having an expensive customized work holding method isn't really going to make sense. So that brings us to the opportunity to create soft jaws. Actually, let me back up really quick. Before I get ahead, what you can see on the right here is actually a depiction of our machining center. It's a 65 3D hybrid. So this is what I would use to do a finishing operation on a part. The fixture that you can see in there isn't really what I was referring to as a custom work holding, but rather more a standardized vise that you would be able to insert the soft jaws into to hold your part. So for the soft jaws, essentially what I mean by when we're saying soft jaws, for those that may be unaware, it's more or less a conformal vise that fits around the outer dimensions of your part. What's really awesome about this nTop workflow is you're able to essentially make changes to your work holding on the fly. So as you can see right here, we have the part laying horizontally. If we decided that we wanted to finish both ends of the part, we'd be able to change the work piece and run it through the same nTopology software to regenerate your soft jaws. And what that allows you to do is basically make changes to your workflow for your final work holding on your part. You're able to change the size and even dimensions, shape of your part without worrying about completely changing your manufacturing process. Furthermore, another piece that's really awesome about this is you'd be able to produce these soft jaws with a subtractive or an additive manufacturing process. So essentially, you could wait until you get to the point where you need to create these soft jaws, see where you have openings in your schedule on either of your machine platforms, and then more or less just tailor which process you use based off of availability within your manufacturing center. Or maybe you could base it off of what you have in inventory for stock for creating these soft jaws. So overall, what we get with this process is through using this software piece as well as an additive and subtractive manufacturing method, we're able to have an agile, quick developing manufacturing method that wouldn't be possible without all three pieces in play. And with that, I'm going to hand it back over to Andrew.
Thanks, Jack. All right. So as Jack said, oftentimes we have people that design these amazing, incredible parts for additive manufacturing. And so here we can see this rocket nozzle that we designed in nTop platform. And there's a problem with it, right? We have functional faces. Those functional faces have tolerances. It means that we can't just additively manufacture a part. That's not the end of our manufacturing story. It's a part of the process, and that process typically includes subtractive finishing operations. But, how do I perform that subtractive finishing? As Jack was saying, we can use soft jaws. So for some relatively simple geometry, like you see on the right-hand side, right, it's fairly easy to put those into soft jaws. But as we start looking at something like a femoral stem, it's not so straightforward about how to go through the design process of creating soft jaws for something like that, right? We can't just clamp this part together. We have a very delicate region with a trabecular lattice structure. We can't just force that together and start crumpling some of the beams in our structure there. And so we need to start thinking about what are the tools that we have available to us to solve those problems. And so nTop platform It's built on this geometry kernel that works with all sorts of different types of data, whether that's your CAD data, your mesh data, or any other kind of information that you want to generate for your geometry. And so that's where this Softjaw workflow came into play. And so if we think about what happens if we want to create these Softjaws, everyone says, all right, let's start out and let's just take, you know, we have this this piece here, let's just subtract it from our geometry. And that works if you have some really small overhangs, but actually, if we look at this part and we see, you know, there's certain regions where if I put my vertebrae in that jaw and I try to remove it out of that jaw, right, we simply can't move it. It's stuck, it's embedded in that geometry. And so this is where a criteria called the removability criteria comes into play, and that we need to look at the direction that we want to remove a part. And then looking at the direction, we can start to remove material from our soft jaw to allow us to easily move that piece of geometry in and out of the jaw itself. And so now we could end up with something that looks more like what we have here on the right, where we subtracted away additional material from the soft jaw to allow us to easily remove that geometry based on a given direction. And so we can just take a quick comparison look here, right? On the left-hand side, you can see the jaw that has a variety of geometry that simply won't allow you to remove our component here. And on the right, we've simply removed all of that away. And that's coming from this removability criteria, which we've applied to the entire geometry of our component, and using nTop platform determined from that what areas of geometry we now need to remove from our soft jaw to allow us to have jaws that easily wrap around our part. And so now I'll jump quickly into nTop platform and give everyone a quick overview of how we can do a few different things inside the software. So to start with, this is my vertebrae part here that I've gone ahead and imported into nTop platform. And so the first step of creating some soft jaws is it's going to be creating the initial geometry that we want to start subtracting material away from. In this case, I'm just using a simple box that represents some of the geometry that I want to now remove material from. And so with my initial vertebrae, I can say, okay, I'm probably going to need to remove some material here, as well as simply booleaning out. But if I just do a Boolean operation, right, I'll end up with material in this region right here that's not going to allow me to simply remove that soft jaw. And so that's where the importance of defining our removal direction comes from. And so now if we open up this conformal jig workflow, we can see that what it takes in for input is this initial parts. We have an initial mold, there's this geometry, and then we have this projection plane. This projection plane corresponds to the direction that we want to move this jig in to add and remove the clamping of this component. And a small feature size tolerance to sample our implicit geometry on. And so now we can see actually the geometry that we end up with. It's this nice jig here. Now the benefit here, right, is I can now remove my part. I'm able to clamp this complex work holding, whether it's something that's biological or designed through topology optimization, you still have the ability to generate work holding for that piece. Now, it's great that I've designed work holding for a single component, but really what I need is this replayable workflow to help me generate a component that I can use for not just this part, but another part. So say I have this simple gear here, right? I may need to do some kind of finishing operation on this, and the same principle really applies here. So I have my gear, I generate the box that's going to fit around this structure, and then I can generate the jaw itself that morphs around my geometry. Now, one thing that's quite interesting about creating the soft jaw is based on the removability criteria, we actually could end up with a design that can be subtractively machined in addition to being additively manufactured. So really you have the full flexibility here of how you want to manufacture this. As Jack said, depending on what your availability is for machines, you have that flexibility to manufacture this part multiple different ways in order to finally finish the main component that you're most interested in. And so all of this, again, is captured through a replayable workflow that works regardless of what input geometry I put into it, whether it's this gear or whether it's other pieces of geometry like a femoral stem. Okay. So at this point, let's, I think we'll open it up for a few questions here. If you do have any questions that we don't answer during this session, please feel free to follow up to us at any of the sources listed below. And let's go ahead and take a look here. Jack, do you have any queued up that you'd like to open up with? All right, I see one of them here from Sean. Are there ways to modify offsets and tolerances? So it's a great question. Inside nTop platform, we have this great ability, because we're working with geometry on this implicit representation, to actually quite easily do offsets of geometry. So say you want to offset your component by a fraction of a millimeter to allow for creating that region where you're going to perform your subtractive finishing operations. That's not a problem. And let's see, the next question here, is there a possibility of unsuited powder left in the printed part?
So I'd be happy to take that one. Sorry, Andrew, my mic was muted. So sorry, I cut you off there. The second half of the question is, could a fracture or break in the part release uncentered powder into the body? So anytime you would use any sort of a lattice structure, you're definitely going to have some powder trapped in your part once you're done. So you would need some sort of a post-processing powder removal process. And there are a lot of different methods that tackle this essentially. My biggest recommendation, especially for very high-end manufacturing applications like biomedical or aerospace, would be to use a dry ultrasonic powder removal process followed by a wet powder removal process using like an ultrasonic bath or something like that. And then typically, I think what most biomedical manufacturers will do is they'll CT scan the parts after the powder removal to ensure that they've gotten all the uncentered powder removed from the part.
Perfect. Well, it looks like that's just about all the time we have today for questions. If we didn't get to your question, look forward to that email from either Jack or myself with some additional information there. And if you do have any questions about nTop platform or Anthropology, again, please feel free to reach out to us at sales@nTopology.com or one of the other channels listed here for Anthropology or DMG Mori. All right, and I hope you all have a great rest of your day, and we look forward to seeing you at our next webinar.